right, good morning, everybody. This morning, we're going to talk about some physics and some signal processing as it relates to OFDM. All right. Now, yesterday when Dobius was up presenting, he made a comment that he's been around for a while, is getting up in the years, and the older he gets, the more he thinks about history. So in that theme, I wanted to show you a picture of what it looks like in Canada. This is a picture from 1901, and what we have here is Guglielmo Marconi setting up on Signal Hill in Newfoundland, and he's trying to raise a kite to receive a signal being transmitted over 3,500 kilometers away in Poldhu, Cornwall. And he's trying to prove long-distance wireless communication. So standing in the cold Atlantic breeze, coming in from the shore, he's trying to catch a signal. It's just a repetitive S being sent via Morse code. And so him and his assistant, George Kemp, are working there trying to capture these signals. Now, at this point in time, just a few years earlier, he was successful at transmitting a signal across the English Channel, right, which is the longest distance that they've done to that point. But in 1901, he's able to achieve this, but there's a lot of people out in the wireless community at that time working in their basements, in their home laboratories, experimenting with wireless signals. One of them was Hertz. Right? And actually waves at this point in time were referred to Hertzian waves, right? And Hertz didn't think much would ever become of wireless and waves. It was just a fun technology to tinker with and play with. But that's what set Marconi apart. Not only was he a brilliant engineer and an inventor, but he had a marketing genius. So I challenge all of you, in order for the technology, the Wi-Fi that we love, in order for people to better understand design best practices, we need to market these best practices out into the community, right? Take it beyond our world so that more people configure better channels, configure better channel widths on their wireless deployments, right? So having that perfect blend of technical savvy and marketing prowess is what led wireless to where we are today. So my name is Troy Martin. My title is Director of Wireless Arts and Science. I work for Ookla, as we learned earlier in the week. It's the company named after a cat. You may recognize me from various webinars that are out there. Feel free to reach out on LinkedIn. You can follow me or connect with me. Now, OFDM itself, it was so spectrally efficient that it became the heart of many modern-day wireless communication systems. So things that we see in fiber optic cables, DOCSIS cable modems, under-the-sea cables, 3G, 4G, 5G technologies, and of course, the Wi-Fi that we know and love. Right? But OFDM itself wasn't really invented or created until 1966, right? When Robert Chang put forward a paper published by the IEEE documenting how we could implement OFDM. But at this point, it was still just a concept, right? We didn't have the electronics or the compute capabilities to process OFDM at line rate to actually deliver the technology that we wanted to implement, right? Actually, before I move on, this is what wireless engineers look like in 1966, right? It was a pretty cool field to be in. So I hope that we've maintained that tradition, or maybe we need to fall back onto how engineers looked in the past. Right. Now here's a somewhat basic concept. It's an example of multipath fading. So you have signals radiating out from an access point towards a client to a receiver device, and in a perfect world, your wireless signals would take the shortest path possible to get that receiving device, right? So nothing overly complicated here. Now, if we looked at it from another perspective, instead of taking that direct path, what really happens is our signals bounce and reflect off different objects, taking many different paths, okay? Which presents a problem in our communication. So before we get into that, let's just step back a little bit and look at this telephone here, which is sometimes a challenge for Gen Z, or Gen Z, I apologize if I speak Canadian here, that if you were to hand a phone to someone from Generation Z, they might not be able to operate it because they didn't realize that you had to stick your finger in and rotate the dial around, right? But what I wanted to talk about is just how digital communication worked in the telephone system, right? So if you were to get your Apple earbuds or a good set of speakers, the frequency response of those speakers would be somewhere between 20 hertz and 20,000 hertz, right? So a fairly broad spectrum of audio frequency. But when we talk on voice systems, we're only talking in the vocal range. And that range is somewhere between 300 and 3,400 hertz, right? So that's the only frequency that we have to send. Now, when we send that transmission, if we believe Shannon and Nyquist, who tried to convince us that to sample a frequency, you have to sample it at twice the highest frequency in order to accurately reproduce that signal. So if our highest frequency is 3,400 hertz, we'd sample it, round it up to about 4,000, and if we double that, that means we're sampling 8,000 times a second, right? And at each one of our samples, if we take a sample and capture a value of 8 bits, we can then digitally represent any analog signal, right? By capturing the analog waveform, we sample it a whole bunch of times, and it turns out that 8 bits per second, or 8 bits times 8,000 samples per second, gives us our 64 kilobits per second, and that 64 kilobits represented the transmission bandwidth of digital communication that we'd see in T1s and E1s and that type of thing, right? Now, as we sample those waves, right, and we can capture what they represent, there is a little bit of an error, right? So as we map them into those 8 little buckets, right, we can only be as granular as our bucket sizes. So if the analog wave is a little bit off that perfect line of our bucket, we get a little bit of error in our digital representation of any analog signal. So it presents a little bit of a challenge as we try to send digital information across an analog medium, right? So now focusing on a high bit stream that we see here across the top, right, we can just represent that with basic square waves, right? It's nothing overly complex. 1 could be a high voltage value, a 0 could be a low voltage value, and we can represent that with these nice perfect square waves. But we can't transmit perfect square waves like this, right? So we can find out different ways to modulate that signal. We can use some phase shift keying where we change the phase of the signal as we transition it from a 1 to a 0. And you can see that in this little waveform, we get 180 degrees shift. Now, this is something that's easy to talk about, but it's actually very hard on the electronics when you have these hard phase shifts in your signal, right? And it produces anomalies which distorts your signals, right? So we want to clean this up a little bit. So we can create some pulse amplitude modulation where we reinvent that signal to make it much smoother, right? So we just put into a different format, a different feature, and we can transmit that. So now our high-speed digital line is being sent by nice smooth waves here representing 1s and 0s, right? But going back to that multipath interference scenario that we had earlier, right, as we bounce off different objects, that same transmission arrives slightly later, slightly weaker in time, right, distorting our original message, making it quite complicated to recover what we're actually trying to transmit. Now, what we can do to compensate for this is we can slow down the signal, right? If that symbol duration takes longer, we can apply some adaptive equalizers, leverage them, and we can recover that signal, right? But we have to talk a little bit slower. So in order to avoid spiraling into a burning ring of fire here, we need to figure out a way to do something a little bit faster, right? And so this reminds me of Stephen Orr's presentation, where he made the comment that people are willing to pay 10% more for speed, but they're not willing to pay to make something 10% more secure, right? So some metrics are perceived as a little bit more valuable, right? Now, if you were just to measure the quality of the pilots from Top Gun based on how fast they could fly an F-14 Tomcat, and that was your sole metric, that might not be very convincing of a pilot's capabilities, right? But if you captured more metrics and looked at a more holistic story to evaluate their performance, you could actually evaluate who is the best of the best. So if we think about this in wireless terms, right, if we had a system where we could perform some comprehensive network metrics capturing, and we could port that and we could evaluate systems or networks based on their ability to deliver superior wireless connectivity, that'd be something that's pretty cool, right? So if you wanted to learn more about this, feel free to reach out to Alan Blake, Matt Starling, or myself, and we could talk more about this program. But getting back into what we're talking about here, FDM and OFDM, we have our high bit stream coming in on the left-hand side. And to slow things down, to take advantage of those adaptive equalizers, we can break up this high-speed serial line into multiple parallel paths. And each parallel path can then be processed a little bit slower in time. We can then code each of those parallel streams, modulate them into a little symbol, and if we aggregate or mux that symbol together, we have a combined symbol of various frequencies that we can then send across the airwaves. Now, because we know what symbols to look for on the receiving side, we can then break this back down and filter out those parallel streams and reassemble everything back together. But the downside of OFDM is that it's not very spectrally efficient, right? We have to put a lot of work in to spread those carrier frequencies apart so that we can recover them on the back end, right? So not a lot of performance gains from FDM itself. So now let's start looking at some waves and seeing what's happening here. If we take a basic sine wave, we can look at it in the time domain, and we can convert it into the frequency domain. So an infinitely long sine wave, viewed in the frequency domain, ends up as a pure spike that's a derivative of that frequency, right? So we can represent various sine waves in either the time domain or the frequency domain. But what we really want to talk about is OFDM, right? What makes OFDM special? Right? So if we try to think of a definition of orthogonal and what that means, one way to describe it is two lines or two planes that meet at perfect right angles. So imagine a floor and a wall, right? Those two planes meet at perfect right angles. That's a definition of orthogonal, but not really helpful for us in communications. In linear algebra, we would define it when you multiply two vectors together. Right? So to define vectors, if you've seen the movie Despicable Me, the supervillain Vector, his superpower is he had both direction and magnitude, right? Two characteristics of a vector. Now, if you multiply two vectors together, their dot product, if it equals 0, that defines orthogonal, right? So there's our simple answer to what it means. I don't really understand what that means, but that's just a result of the formula, right? So that's not super helpful to me. But another way to look at this is if we go back to our waves, right? We can break down these waves, so these infinitely long sine waves, we can break them down to their frequency components. But if we have discrete waves that are bound by time, right? So they're not infinitely long, when we look at those, we get waves that look like this. So they're not perfect spikes in the frequency domain, they're little peaks that have a bunch of little side lobes. Right? And now this becomes interesting because these side lobes were very similar to what we saw when we looked at frequency division multiplexing. Right? Now, one of the cool things about orthogonal in transmitting two different signals is neighboring signals when they overlap. That overlap happens when one signal has a peak value and the neighboring signal overlaps at a null. Right? So you get maximum difference between the peak and the null of the adjacent signal beside it. And by leveraging this property, you can then move these subcarriers, these alternate frequencies, much closer together and gain spectral efficiency. Now, if I was to just pick, let's say, a random number, like 3.2 microseconds, and if I took 1 over 3.2 microseconds, that works out to 312.5 kilohertz, which happens to be the width of the subcarriers that we're familiar with in OFDM, right? So by carefully selecting the appropriate frequency spacing, we can create these waves that have nulls where the subcarrier adjacent to us has a peak value. And that property, that characteristic, is one of the fundamental things about OFDM. And that's one of the things that makes it special. Now, these waves are called sinc functions, right? So here's a little formula that kind of describes that property. One of the things that happens with it, as the longer the time domain is, the more narrow the sinc function, right? So infinitely long time, we have that perfect spike. But if we have a short amount of time, like a short symbol, we get a wider sinc function, right? So they're kind of related to each other in that way. Another cool thing that we have with OFDM to make it work is we have the Fourier transform, okay, which was invented a long time ago. But it's one of those things that it's a neat concept, But there's lots of different ways to solve the answer to this equation. So one of the ways that they do that is by using the fast Fourier transform. So it's just a hyper-efficient technique. Sometimes it's been described as one of the most glorious computer algorithms of our century, or the last century. And the idea that it solves is that you can break down any wave into its fundamental sine waves, right? So if you increase these sine waves at a certain ratio with reducing the amplitude and you add them all up together, eventually you can recreate any square wave or any particular waveform that you're looking at. So now we have the math to make this happen, to be spectrally efficient and then to convert analog to digital waves. We end up with some graphs like this, where we can take any waveforms that are coming in, we can then convert those analog waveforms into their digital representation and process the information that was being sent across those waves, right? So right now, it's been a while since I've showed you a formula, so I wanted to put this up on the screen here. Now, this was an idea that was created by Stuart Riffle, right, to try summarize a very complex thought, right? So in a lot of engineering schools, they allow students to bring in cheat sheets onto their exams, and they cram as many formulas as they possibly can onto these sheets, and then hopefully, during the exam, the idea is you take the right tool or the right equation to solve your problem, right? So Keith talked about having tools in a toolkit, right? When you go on site to try fix a Wi-Fi trouble issue, hopefully you have the right tool in your kit to solve that problem. So equations are just like little tools that mathematically allow you to solve problems. Now, it's summarized like this, and what Stuart Riffle did is he kind of assigned colors to different parts of the formula to try help break it down, right? So for some of you, you may be nodding your heads and like, oh, of course, this makes perfect sense. I understand what all these values mean. There's some text to kind of help wrap your heads around it and explain what's going on. So it kind of humanizes what's going on here. But if you're more of a visual learner, here's a visual representation of what that formula describes, right? So as you spin around a circle, right, as we make this more and more complicated, by picking different points on that circle and changing the size or the amplitude of those circles and how fast they rotate, we can recreate various different shapes of any waveform that we want, right? So it's just a matter of applying the right model to make this happen. So now that we understand all this, and that formula now makes sense to us, now let's dive into OFDM and figure out what makes it special. So we have our high-speed bit stream coming in on the left-hand side. We know that we want to separate it into a bunch of parallel transmissions, right, or parallel streams, so that we can slow it down and apply adaptive equalizers to process and eliminate any of that multipath interference. Now, I've simplified this a little bit here, but in my parallel streams, these 4 bit values, that represents something like 16 QAM modulation, where I can send 16 bits at a time. So depending on the modulation that we're using, we can adjust the bit length in each of these parallel streams, so the bigger our S&R budget is, the more bits we can stuff in each one of those parallel streams, giving us higher rates, higher throughputs, all the way up to 46 gigabits per second, right? So we can finally achieve that, right? And then you can see with the little t there, that time, that corresponds to the time savings that we have coming in, right? So a little property there. Now, I'm only showing 4 parallel bit streams, but kind of extrapolate this out in your mind. Each one of those parallel bit streams would map to a subcarrier, right? So with classic OFDM, we have 64 subcarriers, but really only 48 of them are carrying data, right? Because we have some pilot subcarriers and guard subcarriers, which I always like to imagine the guard subcarriers, right? So back home in Canada, we get a lot of snow in winter, which makes it tough to see the markers on the lane. And so when there's good snow cover on the ground, we can't see where the road ends and where other lanes start. So they put rumble strips onto the edge of the highway. So as you're driving along, once you go far enough out of your lane, you'll hit the rumble strips and you'll hear your car go. So if you can't see the road and you're driving at night, you just put your tire on a rumble strip and you just keep going. And when you stop hearing the rumble, you know you've turned too far left and too far right. So you drive based on these rumble strips, but that helps line you up on the road, just as the guard subcarriers help line up all the important subcarriers transmitting your data, right? Giving you that little bit of buffer, right? So our streams are coming in, we're modulating those sequence of bits using our appropriate Wi-Fi modulation, so BPSK, QPSK, the several different QAM levels that we have. We transform that to our inverse fast Fourier transform. We mux all that together and we send a symbol out into the airwaves. Right, so we got a little, some more numbers here. That 3.2 microseconds, it's coming up again, right? So interesting that I just pulled that out, but it turns out that that's the symbol duration that we use for OFDM. So at this point in time, I just want to take a little aside here, give a shout out to Francois, who's put together these charts and tables that you can find on mcsindex.net, right? So they give you good visibility into all the different data rates and combinations. Two things I want to call out here. One, there's a column with coding. Okay, so that bit stream that I keep talking about, as we carve that out into those parallel streams, we also add a coding layer to that, which gives us some redundancy, some error correcting capabilities, so that the receiver, if something goes wrong, can try recover what the original bits should have been instead of requesting a retransmission, right? So a really useful example of this is if it takes 30 minutes to talk to Mars, right? And we have to send a status update to a Mars rover or something like that. We don't want to send a transmission, have it be corrupted, wait for the rover to not send an ACK back or send us a message that the message was corrupted, and wait another half hour for that. And now it takes an hour to have a conversation in both directions, right? If the rover could correct the original transmission, we would avoid retransmissions. Right, so that's one of the savings, the gains there. The other thing that I wanted to call out, because we're talking a lot about math here, is up across the top of this chart, there's a little tab that you can click on, which says the math behind it. You click on that tab, it takes you to some references from the IEEE documentation. Now, it's been updated, so what you're seeing here is some of the OFDM-A-based calculations. But these are charts and tables that come directly from the standard. But this is how the data rates themselves are calculated, right? Which I'd argue kind of sit on top of what we're talking about in terms of the RF fundamentals and the signal processing that's happening in OFDM, right? So just a little aside there, right? So jumping back into this, right, we have our little symbols that are hurtling through the airwaves, right? And as each symbol gets sent out, we need a gap between the first symbol and the second symbol, right? We need a little gap in time so we know where one starts and one ends, right? So we put this little gap in here and we call this the guard interval, right? Now, the transmission on the top looks very clear, very crisp, but if we think back to where we started a few minutes ago, talking about the multipath reflections, as those reflections come in, it starts distorting all those symbols that we're receiving, right? And now it's a little bit harder to make sense of these symbols coming in. And if there's too much reflections, right, we can't tell when one symbol starts and one symbol ends, right? So it becomes quite confusing. So we need a way to try resolve and solve this, right? Now, thinking about those telephones, right, and our quantization that goes on there, if we have a symbol like this, it's relatively easy to map that analog waveform into our digital buckets, our digital bins, and figure out what's going on, right? But one of the tricks we were using, or I was showing earlier, is to differentiate where one symbol starts and one begins, is we drop the signal level down to 0. And when we do that, and then map that onto our bin values, we waste a lot of granularity in our signals, right? So we lose the ability to be more precise. We introduce more error into our decoding, into our demodulation, or our coding into an analog waveform. So it becomes a little bit problematic. And so we need to figure out a way around this. So this is where cyclic prefixing comes in, right? So the idea here is, what if we were to copy the first portion of every symbol? And if we copy that, and we'll just kind of extrapolate it, lift it up there a little bit, and we move that to the end, now instead of dropping down to 0, we maintain a more constant level for our transmission. Right? Then we don't have to worry about dropping down to null. We get more precision in our transmissions. And this reduces a lot of error that we would see in our transmissions, right? But it's not all blueberries and butterflies, okay? There's a penalty for doing this, right? So if we look at 802.11a, and this is where I used to teach a lot of classes, and I was teaching in the South US, and they kept asking me why I was speaking Canadian all the time. And I couldn't figure out what they were talking about. It was like, you keep saying 11a. And I'm like, yeah, the standard A. And they're like, no, you're doing it again. So whenever it said 11 A, B, G, N, A, C, they kept thinking I was throwing in Canadian. And as a complete aside, with spectrum analyzers, I find a lot of people in the Wi-Fi community shorten it because spectrum analyzer is a really long word. They'll say spec-an, right? And we all know what we're talking about. But in the cellular world, and Ferdet talked about the 3GPP organization, so sort of the cellular equivalent to what the IEEE is doing in our world. The cellular folks, they like to say spec-A. So I go for beers with a fellow peer who's a big cellular guy, we get into big debates and fisticuffs over which technology is better. And so I started using spec-A so that we might get confused about what we're talking about. One, it makes me sound more Canadian. Two, I find sometimes talking to Wi-Fi folks, I get corrected that it's not spec-A, it's spec-N. But I think it gives you some insight that when you hear people say, spec-N, they're coming from a Wi-Fi background. If they start talking about spec-As, they're coming from a cellular background. So as we start to see more converged architectures, we integrate, moving from inside buildings, outside buildings, using these different technologies, which are all, again, fundamentally based on OFDM. As we use them, I think it's really important to kind of get some insights and some perspectives of where people are coming from. Right. So again, we lose about 1 dB by adding this. And that cyclic prefix in that guard interval, the duration of that is 0.8 microseconds. So the symbol plus the guard interval gives us our 4 seconds, right? So every symbol duration, which is guard interval, gives us 4 seconds there that we can see. The guard interval and that cyclic prefix, we've decided we need about 25% of the symbol duration for the guard interval, right? So as we evolved into OFDMA and our symbols got longer, so did the guard interval, right? So we can maintain that 25% gap in between those symbols. So the benefits of cyclic prefixing, we can see here on this little slide, right, on this chart. The picture on the right-hand side, the little X on the left-hand quadrant, that's the symbol that was better represented because we're able to use cyclic prefixing. The image that we see on the left-hand side, that's the error that would have resulted, right, which would have ultimately driven a retransmission, again, consuming more airtime, slowing us down. Right? So that's cyclic prefixing in a nutshell. So to kind of wrap all this up and summarize what's going on here, right? We have our high-speed serial bit stream coming in, right? We do some line coding to it. We separate that into parallel streams. Each one of those parallel streams we then modulate, right? Based on our Wi-Fi modulation schemes that we're fairly familiar with. That modulated symbol, we then run an inverse fast Fourier transform. Right? So the inverse fast Fourier transform is where we take a digital code and transform it into an analog code. Right? So that's the inverse direction. The fast Fourier transform is just the opposite application of that. So it's taking analog to digital, right? Which will happen on the receiver side. Right? So once we have that, our serial, we mux everything back together, all those separate parallel streams. We create our super symbol, that I'll call it. We send that out across the airwaves and it hurls through space, bounces off a bunch of different reflections, ultimately, or reflective surfaces, whatever it is, ultimately gets received by the receiving side of things. It removes that cyclic prefix, right? Breaks down what it received as a serial communication, separates everything back out into those parallel streams, right? So all of our different subcarriers that are spaced 312.5 kilohertz apart, separates all those out, right? Demodulates everything, reassembles all those parallel streams back into our super high rate linear signal, right? And then that's all the bits, that's the code that we're receiving from our transmitter, right? And that's a little description of how OFDM works in a nutshell, right?